Okay,
Hi,
thank
are
you.
you okay?
Thank you, Moiko. Now we will start our challenge for Middlesex League 2021 RCAP. First, I will explain what we will do in this challenge. For this year, because of the reason of COVID-19, we have to organize this competition online. So for Middlesex League, we have almost the same method to organize the competition as a international RoboCup competition 5 months ago. So we have two challenges. The first should be the scientific challenge. In this challenge, the team could wait a minute. In this challenge, in scientific challenge, the team are free to show one significant achievement, and the other teams and two members from the EC and the TC will evaluate all the teams. And in the video challenge, the video should be more than 5 minutes, and the technology is already be published to all the team leaders. So first, we will have the scientific challenge. According to the order we have drawn in the team leader meeting, the first team should be. Okay, now we will start our scientific challenge. The first will be Dagozilla ITV from Indonesia. So now I will invite all the team leaders or team members into the competition room and get ready for their challenge. So team leader and team members, anyone you will take part in the challenge, please go into the challenge room.
Thank you, Faye. So Dagozilla ITB, please move to the competition room. Thank you.
Hi there.
I can hear you.
Hello? Can you hear me?
I can hear you very clearly.
Oh yeah, sure. Thank you.
We will also have our live broadcast on the YouTube and have already published to the team leaders. And you can also get the link from the website of RCAP 2021. For team Dagozilla, the challenge will start 1 minute later. Oh, sorry. According to the timetable, the first team presentation will start at 10 past 14 Japan time. So you still have several minutes.
Sure, thank you.
If anyone want to enter the competition room, please change name first. According to the rules, please enter the team name before your person name. I see someone in the waiting room, but I can't. I don't know which team he is. Anyone who want to enter the competition room, please change the name with the team name first before your personal name. Thank you. So Team Dagozilla, are you ready?
Yeah, I'm already ready.
Okay, now I will stop share my screen and you can stop share anything you want.
Let me share my presentation.
Yes, please.
There you go. If it already loads, can you see?
Have you shared your screen?
Yes, I have.
Wait a minute. Okay. I can see your screen, but there is nothing. You didn't play the the PowerPoint? Okay, I can see the.
Can see, yeah.
Yes, I can see that.
Sure.
So it's your time. Please.
Sure, I'll start. Thank you for the change. Thank you for the time. Hello, I'm Bimo Etialaman Putra from the Godzilla ITB team. I'm here to present our team scientific challenge. It is about modified bias filter to integrate out of sequence measurement data. Now, here is the table of contents. It contains 4 parts, which is introduction, proposed solution, experiment, and the conclusion. Now, here is the problem introduction analysis. So, as you all already may be aware, here is the RoboCup objective, which is to develop an autonomous humanoid robot soccer teams, which can win again the winner of the most recent World Cup by 2050. Now, to achieve this goal, we certainly need intelligent and adaptive robots that cooperate together, where communication and robust information sharing is key. Especially world state estimation should use data from all robots to overcome single robot sensor limitation. Now, nowadays, actually, it's quite standard for MSL robots to share information with each other, but so far we are in an idealized, unrealistic environment. Now, what if we are in a condition where there is unreliable network with high latency and lots of drop package? For example, we are in a huge stadium with lot of viewers, with lot of Wi-Fi, lot of tethering, with Wi-Fi interference going on. Or maybe we use other kinds of transmission data, for example, voice, which certainly transmit less data over time. So with that, in unreliable and high latency condition, how do we handle late and out of sequence data to maintain information sharing robustness? Now we think that this is a relatively underexplored problem in RoboCup circles. Now here's part 2, proposed solution. First, we consider the common filtering algorithm used in robotics, which is bias filter, used for estimation and tracking. As we all may be already aware, bias filter is a probabilistic algorithm where we use the 2 model, transition model function and the measurement model function, to integrate control data and measurement data to our world state distribution. And there are popular variants including Kalman filter and also particle filter, which use a cluster of particles to model the distribution of the world state. Now, basic bias filter cannot integrate out of sequence measurement data in its basic variation. By that I mean data which is older than the newest processed data. Why? Because then the Markov assumption cannot be used there, and we need all the estimation distribution before the time of data. Now, actually, in different fields in electrical control, actually there has already been multiple research about this, but they do it under the constraint of limited hardware storage, and they use some kind of added assumptions or approximation or smoothing function. For example, they estimate the old distribution using the current one and cache measurement data because they cannot actually store the old distributions because of the storage limitation. Now, in our case, actually, the trivial solution works well. Here we propose the simple modified bias filter, which just cache both old measurement data and estimation distribution for the past few measurements. Here, for our case, this is viable because modern PC can handle the linear increase in space and time complexity. This method is preferred because it is simpler and actually faster in its complexity. It's still mathematically correct, and we don't need to use any additional assumptions or approximations. Now, here is the pseudocode for the modified bias filter. Basically, there is the filter function here, and the modified filter just use records, which is a multi-map using time as its key and distribution and data as its value. And then we just find the newest older distribution in the records. And after we integrate the newly acquired data, we just recalculate all previous distribution after that, and then return the newest one. Here is the related data to be estimated in our case. For example, from our visual perception, we can perceive the ball, the landmark, the other robot's position. And for control, we can find odometry, a displacement of the robot, and compass orientation, and also information from other robots, obviously. From where we need to find the robot's motion, which is the pose and the twist, and the ball motion, which is the position and the velocity of the ball. Now, so from here, the natural solution in ROS architecture consists of 3 callbacks, which is the sensor data callback, the frame chart data callback, and the computation parent event. Now, because of the latency problem where data can come late, we should handle each data separately without waiting for other data availability. And also we need to couple each data with a timestamp so that we know if a data is late or out of sequence. For sensor data, we can use sensor data to estimate our own motion using IMCL and the ball motion using augmented if we see the ball, or friends motion if you see the friends. Some of these results can then be broadcasted, for example, our motion and the ball, to be received as information by other friends. Well, data from friends can then also be used to estimate the friend's motion from his localization result and then the ball. Now, the IMCL of a robot use multiple different data, for example, odometry and landmarks, and then just one visual perception, so it's generally more reliable than our perception of the friend. And word model also needs to publish estimation result for every computation periods, which in our case is around 30 milliseconds. So timestamp attached to each data is actually useful in this case to correct the estimation, to produce the most up-to-date estimation we can have using some kind of prediction, using the difference between the current time and the timestamp. So the modified Bayes filter, the new algorithm, can then be used here to integrate our ball perception and friends ball data, and also our friends perception with a friends localization result. Now for the second case, we actually need two different interfaces with different measurement models, and also some kind of assignment algorithm to identify each percepted friends ID. Now here's the experiment. So we develop an idealized simulation environment to simulate real-world state, sensor, and communication with latency in ROS nodes, where each algorithm will then be evaluated for 5 times 3-minute simulation, or around 30,000 data points, and analyzed based on their statistics such as medians and upper quartile like that. Here are the nodes. There is the world state simulator, which simulates the robots and ball motion using some kind of simple planar and physics. Sensor simulators, which simulates each robot sensor with some kind of error profiles in independent Gaussian distribution for each component. And then here is the communication simulator, which relays communication. Now it's modeled as two-state hidden Markov model, which state stable and unstable condition, which their own distribution of the latency and the message drop change. And then there is 3 simulation scenarios based on stable network condition percentage, where good is 80% stable, moderate is 50%, and bad is 20%. And last is the evaluator, which evaluates algorithm accuracy based on error in estimation in matters between estimation and the true world state. So we create 3 setup, which is the baseline setup, where we discard out of sequence ball data and rely only on communicated localization data for friends motion. And for improvement development feature 1, we integrate out of sequence ball data from friends using the modified Bayes filter. And for development 2, we integrate friends localization data with percepted relative friends position with the modified filter 2. Here are the results. For development 1, we can see from the graph in the orange box plot that improvements are more significant in better network condition. Why? This is likely because out of sequence frame data exists when we are also perceiving the ball. So it's hence badly delayed ones of the friends ball data will not bring much impact because we already perceive the ball. And for the second improvement, conversely here, improvements are more significant in worse conditions. Why? Because in good network condition, if friends localization result is available on time, it's a much better estimation, as we said earlier, than our visual perception. But if not, visual perception will really help correct the old localization result. And for the fourth part, the conclusion after this, so we have shown that the use of the modified Bayes filter can decrease estimation errors in condition evolving network latency. And for future works, some ideas we suggest include augmenting and validating the ideal simulation data with real-world experiments. Also try to correct our localization results with other friends' perception of us. And also try to broadcast the whole estimation distribution rather than just a single data point. And maybe try other filter methods such as Kubatur-Kalman filter and neural networks maybe. That's it from me. Thank you. Here's my profile if you have any question. Thank you. I'll give it back to the moderator. That's it for me.
Okay, thank you very much. Now it's time for the questions. Please, question time. Thank you.
So I have a question about the experimental result. It's okay?
Yeah, sure.
Yeah, you experienced in the three situations, the good network and the moderate network and the bad network. I cannot understand. This is what is different to this network.
Yeah. So as we said earlier in the communication simulator setup, I'll explain more about this setup. So there is in bad network conditions, there should be some kind of latency between robot communication and some change of message drops. Now we model the communication network based on some paper as two-stage hidden Markov model. So basically, the network condition in a given time moment can be stable or unstable, where each condition contains their own distribution of the delay, latency time, and also some message drop. As you can see in the right, actually, we can see the parameter we use. So in the stable condition, the probability of a message being sent is 95%, and the delay latency, where it's modeled as a shifted gamma distribution, have mean of 35 millisecond, standard deviation of 10 millisecond, and minimum latency of 20 millisecond. Now, in unstable network condition, the send probability is just 35%, where the delay mean is 300 millisecond, the standard deviation is 100, and the minimum latency is 150 millisecond. Now, because it's hidden Markov model, we can actually tweak the percentage of when the network is stable compared to the unstable network condition percentage. So by tweaking the hidden Markov model change, we can set three scenario where the good network condition has 80% of a stable network condition time, moderate have 50%, and bad have 20%. If that answers your question.
Okay, thank you very much. So this is some simulation situation. Yes, that's right.
Yes.
So if you are using in some real situation, what is expect to some result of which condition is much which condition is most fit to the good condition or moderate condition and the bad condition if you're using the real robot?
I'm sorry, I can't quite catch your problem. Can you repeat for me? Thank you.
Okay, so maybe this is a simulation situation.
Yes.
So if you are using to the HMM model in real robot, how what accuracy what accuracy do you want or do you expect to utilize this kind of modeling?
So we actually measure the metric of the performance by improvement. So as you by error in matter, so we use error as our metric. Here we can see in the graph, we can see the estimation of each robot. We name the robot alpha, beta, gamma, and each estimation, each robot generate their own estimation of the alpha position, the beta position, the gamma position, and the ball position, as you can see. So the metric use matter, right? Using the distance of the estimation and the true world state. In real world simulation, actually, if we consider the difference between the simulation condition, first, actually, I think that our current robot condition have much better range in its vision, and as such can get a lot more landmark data rather than the one in the simulation. So I think that for the localization, it should be lower than this, the results shown here. But certainly there will be some, I think the error will not be Gaussian. Certainly in real world condition, the error will not be Gaussian independently distributed, right? So I think the ball, which use only one data point, which is the visual perception, will be higher in error. But I cannot actually give you some real numbers because we haven't actually set up some kind of testing, accuracy testing in our real world environment. It's quite tricky.
Okay, thank you very much.
Okay, thank you, Team Dagazilla. So now it's time for the next team. So could you please leave the competition room and go back to the open room? Thank you.
All right. Thank you very much for your time.
Thank you. You can stop share.
Yeah, I'll leave the room. Thank you.
Next team will be RV Infinity from Japan. So Team RV Infinity, if you are ready, you can start your challenge. Now I will stop share my screen and it's up to you to show everything you want. Thank you.
Okay, can you see my slide?
Yes, please.
Thank you. Okay, can I start?
Yes, it's your time, please.
Thank you. Hello everyone, I'm Yu Hangma from RE Infinity. Today I would like to talk about obstacle detection method applying the human selective attention that we use in our robots. I will start from the introduction. The recognition of the dynamic obstacle is a very important function for autonomous mobile robots. The ability to correctly identify the position of multiple obstacles in real time affect robots' strategy and the path planning, and even the robot's safety. So this study was performed to construct a detection system capable of recognizing multiple obstacles in real time. About our vision system, we use an omnidirectional camera and a depth camera and a LiDAR to get the environment information. About the detail of the sensors, we will introduce later in the video challenge. By integrating information from multiple sensors, we can obtain the auxiliary environment information. And we use omnidirectional camera to identify the self-position and three sensors to determine the position of obstacles. Then we synthesize the self-position with the obstacle information to get the position information of the obstacles. However, the self-position obtained by the omnidirectional camera will contain a certain amount of error. In order to integrate variable errors in the position information, we use the Fermi-Dirac distribution. Generally, the Fermi-Dirac distribution can be used to represent the distribution probability of the electrons, which has the property of the spreading with the increasing temperature. In here, we use the Fermi-Dirac distribution to represent the variation of the error with the distance. After applying the Fermi-Dirac distribution, we generate a probability space from the obstacle information obtained by a single robot, like this. After that, we generate a combined probability space by aggregating the obstacle information obtained by multiple robots. When combined the information obtained from OT robot, we generate a probability space where only opponent robots exist by removing the fitness value with with the center range of the teammate robot's position, like this blue circle. So the generated probability space has a multiple maxima, and it is difficult for general search method to find all the maxima in the real time. So here we adopt the concept of human selective attention to find all the maxima in real time. The human visual system does not have the ability to process all information taken by the eye. However, we can recognize visual surrounding information unconsciously in real time. That's because human visual system can throw out unnecessary information and reduce the load of brain. We call it selective attention. The selective attention consists of two elements. One of it is active attention. When we look at the given object, we only pay attention to a narrow area, like this blue robot. On the other hand, we can notice objects that appear into the view suddenly, like this ball. We call this passive attention. Selective attention simultaneously relies both the narrow area attention searched from the carefully and the wide area attention searched for roughly. We propose a detector system consisting of the attention GA based on selective attention, which consists of random searching as a rough searching and an improved GA searching as a careful searching. When the fitness value of the searching point, like this red point, exceeds a threshold, the position of this candidate point begins to care for searching, like this black point. This algorithm follows the following formula for the allocation of the computational resource. Since the value of our searching point, PA, in this, it's a fixed value. So when the only few groups of GA exist, like this picture, the searching system has a high performance for the finding a newly appearing target. On the other hand, when there are many groups of GA, the searching system has a high performance in order to detect multiple targets. So we can see this is a trade-off relation between the performance for finding a new target and detecting a multi-targets. Finally, we performed the performance verification experiment. The size of field is 6 × 8 meters. And this experiment using 2 robots and 2 moving obstacles. We confirmed the recognition result in real time on the screen of the coach PC. So this video shows the result of our experiment. As you can see, our robot detects the position of the 2 obstacles in real time successfully. Here's the conclusion. We have developed an obstacle search algorithm based on human selective attention, and we applied the algorithm to soccer robot and achieved real-time recognition of surrounding obstacles. That's all. Thank you for your attention.
Thank you, Team RV Infinity. So it's time for the questions, please.
Hi, I have a question. Yeah,
Please.
I have a question. Yeah, in your slide, you said that active selective in the last in page 8. Yeah.
Page 8. Yes.
Yeah. Active attention. Yeah. Active attention. But in your in your experiment, yeah, I don't set the robot run to find the obstacle. Yeah, the real robot is static.
Oh, thank you for your question. Oh, I see. Yes, we told this video for a long time ago. So that's right. So there is only the active attention. There is only the active attention in here. I'm sorry for that. So so I will for that's a miss for this video. But in the we use this method in the real game for a long time. So it is worked it is worked well in the real game. I'm sorry for this video. Did not show the passive attention.
Yeah,
Thank
yeah.
you.
I just yeah, it's okay. I just I just interested in yeah how the robot to active to find or dynamic obstacle. I think it's very interesting. Yeah, another question is that yeah in the slide you mentioned that the robot is detector. The robot detected the obstacle by integrating 3 sensors.
Yes.
Oh, yeah. But how about the error? How about the detection error? The measurement error of the 3 sensors.
Okay. I see. We use these 3 sensors to find the obstacles, but about the robot self, the self location is only by use the omnidirectional camera. So our omnidirectional camera have a lot of error about to get the location. So on the video challenge, we will say the sensors error. So it is so it has a big error in the self location. So it is we get the obstacle information by the self location. So that is many of error in the in the last.
Yeah. Okay.
About
okay.
about 20 centimeter.
20
think.
cent. Yeah. Okay. Okay. Thank you very much. Thank you very much.
Thank you very much.
We still have time. Any more questions?
We want to ask something. We're from Iris. Okay, thank you for the time. First, you have tried it on your real robot, right? But in this case, you are using a sweet case. But have you ever tried this system on your real robot with another robot as its opponent on a real game? And we want to know how accurate this method is. And next, what's the usage of your depth cam? Because you are using a omnivision cam and a depth cam. Because in our opinion, the omnicam can see the entire field. Okay, that's all. Thank you.
Thank you for your question. The first question, yes, we use this in a real game for many years, and I think it is worked well. So about the time we in the obstacle when there is many of obstacle, the time will more longer, but the longest time is less than 13 milliseconds. So it is real time. It is working real time. So I think it's no problem. Thank you.
So, any more questions?
Okay, excuse me. How about the second question about the usage of the depth cam? Because in here you are using a omnivision cam and also a depth cam. Because in our opinion, omnivision cam can see through entire field. Can you please answer that? Thank you.
Okay. We combine the obstacle position information in the coach PC. So in each robot, they just get the information from sensor and get the position from this robot and transfer the position to the coach PC. So we can use a high performance PC for the coach PC. So I think the time. Sorry, I can't tell you the time exactly in here, but it is enough for the real time game. So thank you.
Okay, thank you so much for your answer.
Okay, thank you, Team Infinity. If you finish your challenge, you can go back to the open room, and the next team should be the Iris. Team Iris, could you please go into the challenge room? Thank you.
Thank you very much.
So Team Iris, are you ready?
Yes, we are ready. Can my friends share the screen?
Okay, thank you. Okay, I have a stop share my screen. You can show everything you want.
Okay, can you see my screen?
Yes, I can.
Okay.
So if you are ready, you can start your presentation now. Thank you.
Okay. Good afternoon, the honorable participants on this Zoom meeting or even on the YouTube live streaming. We are IRIS, and IRIS stands for ITS Robot with Intelligent System. But before further ado, let me introduce myself. My name is Danendra Klevero Ananda, and I will be happy if you call me Danen. And I'm here as a representative of IRIS. And I will present to you and glad to discuss with all of you about our presentation. IRIS itself is a robotic team in Institut Teknologi 10 November in Surabaya City, Indonesia. Right now, IRIS has 22 active members inside the team with 4 divisions: programming, electronic, mechanical, and official. And in this beautiful day, we would like to present to you and glad to discuss about our research about methods on increasing goal probability. First, we'll talk about middle size league. What is the purpose of it? Middle size league itself is a 5x5 robot competition which aims to score goals as much as possible. The winner will be determined by most goal. But there is a thing that we want to solve. The thing is, right now, at least 30% of robot shot can't score any goal. It's deeply regretted because the chance to shoot is a very rare chance. It would be a big advantage if robot could maximize this opportunity. And you have seen robots failure on making score by this video. Then, a question will come up to our head about how to increase the scoring probability from robot picker. Now, let's see some upcoming video clip. First, we have the long range kick by some football player. All of that kids are aiming to the same direction. It is the top corner, no matter the top left or the top right of the goalpost. From all of that shot, we could take a conclusion that there are two main keys on scoring goal to goalpost. First is a powerful kick, and second is a ball direction. And according to analysis of torques and forces applied on free kick in football 2010, the minimum ball speed that required to overwhelm the goalkeeper is around about 50 km per hour. There are a lot of factors that take effect towards the generated ball speed, like foot weight and foot center of mass from distal point, etc. But the most influential factor is how much power given to our ball. Kicks that are difficult to predict are kicks that have an intersection angle. To make the ball have an angle of intersection, a soccer player must kick the ball at the center mass point of the ball. Then, the ball is kicked sideways using the inside of the foot, causing the ball to spin. When the ball is moving, the air will be in the opposite direction of the right. When by shooting the center of mass of the ball, it would be better. Why? Because there will be no energy that being converted to spin. The kick that would make the goalkeeper overwhelmed is a kick that aiming to the farthest point from the keeper and aiming to the farthest pole at the same time. In this case, it's the top left or right corner of our goalpost. Actually, this technique has been discovered before, but sadly, it's still hard to implement this technique in real life due to some reason, like player skill. And now, the question is our robot ready and capable on doing this kind of test? To make it happen, we still need some more improvement, either from the hardware and even the software. First, we need to improve our kicker. Previously, our robot uses brushless motor with gearbox to increase its torque. You can see our old kicker in your top right screen, but this method has some disadvantages that it is not fixed, so sometimes it could detach from our robot. Sometimes it also hit a robot's cable, and the kicker sensor are not that sensitive, so sometimes it doesn't detect any kicker motion. Therefore, we changed our system to solenoid, and we are aiming for 17 Newton meter of torque value. Therefore, we use the following equation that you can see in your screen. From these references, we also get very good solenoid specification to be applied as kicker, and we have implemented them to our robot with the following specification, which you can read in your own screen. And to decide the kicker's direction, we will need goalpost and goalkeeper's position. Therefore, we add camera sensor to take the visual data. We use webcam because it has a wide angle and automatic low light correction feature, which help goalpost detection. From our webcam data, we would proceed through two steps of verification. First, we will use YOLO classification, and in this case, we are using Tiny YOLO version 5. Why? Because it's lighter and have a higher accuracy. Then, we will add filter to verify the data to prevent a false detection. Here is some technology set up to generate the desired output, and from the left side, there are kicker, camera, and kicker test using solenoid. First, we have our processing technology. From this classification, it will decide the direction of the ball to the upper right or left corner. This position will surely overwhelm the keeper. Next, we have field system testing. We use some different variation of robot to goalpost distance to test our algorithm flexibility, which we have developed before. We also add humans role to pass the ball to test the robot's speed and latency when it sees goalpost for the first time. Our algorithm with YOLO could classify some object like goalposts, robots, right top corner, and left top corner with accuracy up to 95%. And to prevent false detection, we also use additional filter to verify that it is a goalpost and not a normal ball. And we also use a fuzzy controller to set the ball's direction to top left or right corner. This algorithm is important so that even the robot has a different position, the top corner kick will be stable. Besides, we also use capacitor discharge voltage variable because the kicker speed depends on it. And you will see a table here, and here is some track record of some different distance and height variation, and also some encoder variation. The graph that you see here is the distance and capacitor voltage comparison. The top corner left and right look almost the same. From all the 40 tests are able to make a score, which leads us to a conclusion that it has accuracy up to 100%. So, how about coaching a real goalkeeper? Before that, we have to set some systems that we would use. We have to make a class that has a person, goal, top right, and top corner variable. Then, we set the target to 2x3 footballs goal post size. We also need to tune our capacitor discharge voltage and position encoder to match the 2x3 goal size. Our subject is an amateur goalkeeper from Temanggung Futsal Club. Our target is to determine the weakness of the keeper. Based on the statistic of some random kick that done by our robot, the direction would be the top corner to overwhelm our goalkeeper. And we have divided our goalpost to 9 parts to define the keeper's weakness. And the upcoming video is a video of our goalkeeper praying with our robot. From all of that test that has been done, we can make a conclusion that our goalkeeper has weakness on goal number 1, which means it is the top left corner. Last but not least, we can take a conclusion that the success rate of goals can be increased by increasing the power of the kick and directs to the far post, so that it is difficult for the goalkeeper. And by using robots and deep learning, futsal goalkeeper can be trained to determine goalkeeper weakness and improve reflexes. And for future development, we will make a design of a goalkeeper training using this system with a wider scale. And in this case, it's a football goalkeeper trainer. And we think that's all we got for today's presentation. Thank you for your attention, and if you have any question, feel free to ask us. Thank you.
Thank you very much. Thank you, Team Iris. Now it's time for the questions.
Hello, I have a question.
Okay.
Yeah, how about the runtime performance of YOLO 10 with 4? Yeah, deep learning network.
Okay, thank you for your question. So, with using this YOLO, we have 4 classes which we have presented before, and we use 500 dataset on it with 25 convolutional layer that has been trained for around about 2 days. Is that answer your question?
Okay. Thank you very much.
Okay, thank you for your question.
I have one question, it's okay? So I very interested in your some kicking device. Maybe you're some making the very strong kicking device. So do you some calculate how strength in some thickness or something in the kicking devices? So that means so you are changing to some length or something in the kicking device. So what is different about some strength about the materials or something?
Okay, we are using this specification which has coil length of 120 millimeter, inside diameter of 40 millimeter, outside diameter of 56.8 millimeter. Copper type is AWG16, which it is 1.29 millimeter. It has turns 104, 1400 and layers 14. which could make a torque power to 17 Newton meter.
Yeah, very big. So this is if you many times is kicking is okay. So is the material or some kicking devices. So especially the actuator.
Yes, it's okay because of the material. It's the best hardware till now.
Okay, thank you very much.
Okay, thank you.
Any more questions?
Excuse me, we're from the Gusila ITB. Want to ask question?
Okay, thank you. Go on.
Okay. Why do you need to detect the goal post? Because given we already know our robot position and we also know the keeper position, and why do you need to even detect the corner of the goal post? We think that's an overkill. That's overkill. Thank you.
Okay, is that all of your question?
Yes.
Okay, may I confirm you have asked about why do we need to detect that goalpost, right?
I'm sorry, the corner, the left corner and the right corner of the goalpost, because we already know all the dimensions of the goalpost.
Okay, we are detecting the top left corner and top right corner to determine where is the direction of the ball that our robots have to shoot. So yeah, that's the answer.
Is because you already detect the goal as a whole, and you can know which part of it is the corner left and which part of it is the corner right. Isn't that enough?
Yes, it is.
So isn't that a double detection that you already know the position of the goal as a whole, so you know the corner, but you also detect the corner again?
We detect the top right corner and the top left corner to determine where is the empty space where there is no keeper in there, because we are training a keeper, right? So we have to choose the position where the keeper will feel overwhelmed. Where, for example, if the keeper is on the right side, so the robot will kick to the top left side. And if the keeper is on the left side, a robot will kick the ball to the top right side.
Okay.
For the conclusion, it's for decision making.
All right. Thank you.
Answer your question.
I have some questions.
Yeah, go on.
You set the part of the goal to the 9 apart, right? So your shooting motion is selected with the 9 part of the goal, right?
Yes.
So have you ever considering the goalkeeper's emotion?
Okay. We have divided that goalpost to 9 part based on a journal that we have read, and also for making a motion on that 9 part. For now, we haven't tried it yet, but it could be our next research. Thank you. Is that answer your question?
Okay. Yes, thank you.
Okay, thank you very much.
Okay, thank you, Team Iris. If you finish your presentation, you can go back to the open room. Thank you. Next team will be the Hibikino and Musashi.
Thank you very much.
Team Hibikino, Musashi, can you hear me?
Yes, I can hear your voice.
Are you ready for the challenge?
Yes.
Okay, you have still more than 1 minute left.
Okay.
Okay, Team Hibikino Musashi, I will stop share my screen and it's your time to show what you want.
Okay, thank you. Can you hear my voice?
Yes, we can.
Thank you. So I'm Moeko Tominaga from Nippon Institute of Technology. I will now present the scientific challenge of Hibikino Musashi under the title of Research for Symbiotic System Between Humans and Robots. Our goal is for humans and robots to be able to play soccer together as a team, not just against each other. So we have been looking at the ways to use color and shape to recognize humans. As a communication system, it is difficult to adapt the communication methods used by robots to humans. Therefore, in the near future, we will need a system that allows robots to determine their own actions based on human behavior. This is exactly what we are aiming for in our communication system. In previous research and development, we have succeeded in getting robots to choose their actions based on international triggers issued by humans. The next step is to select one's own behavior from the implicit behavior of others. This research aims so robots predict human behavior and decide their roles. Here are some suggestions on what issues to work on. First, how to recognize the implicit behaviors of others. Roles and behaviors determined implicitly was predicted based on experience. Also, the team is making decisions based on shared tactics. So, what do you think are the actual decision-making factors? Maybe location of others and ball, and the speed and the direction of movement, also score and elapse the time. So we tried to clarify the determinations of behavior by clustering the factors that determine what a human or robot decided to do using the TensorSum. It's a neural network. So from this study, we see the following benefits from ephemeral decisions to organizational decisions, and to acquire implicit cooperative behavior with humans. Also from individual skills to team tactics. Why do we use clustering method? I will explain how to use clustering methods for decision making. Ordinarily, the characteristics of TensorSum is using clustering ability. This system can visualize and map the simulation situation in a clear way. And also using the interpolation function, we don't need this input full situation in the game. We finally devised a system that can output an action when a state quantity clustering of many variables is input to TensorSum. By the way, have you ever heard of some self-organizing map? From this sum, we get a two-dimensional map called the future map. For example, if we use this clustering machine based on animal future data, clustering will be done without using a teacher, as shown in the figure on the right. So around here is a bird, and around here is not bird. So the TensorSum that we use in this project is an extension of this sum. If the input data is tensor type, the output map will be in the form of a tensor slice. For example, using data on multiple people's preferred drinks and their situations, drink preference by age and changes in drink preferences by situation can be clustered. Now, I choose the situation of working at a desk here. The result shown, the young woman prefer coffee or some tea. But when I choose the party time, we found that they prefer juice, such as cola or ginger. So this color is high demand is red and low demand is blue. Using this method, the idea of this research is to do clustering by inputting the situation and player and the state quantity and behavior. We did two experiments. The first was to learn human behavior. The input data were state quantities obtained from videos taken with a video camera. The second was to learn the robot behavior. The input data is the logging data of the robot match. And the third is still in processing. For the first study, we collected the data by photographies players who had experience in futsal. The purpose is to clarify whether the load of each player in the team is shared by the whole teams. This is the environment viewer. In this diagram, each team is shown in red and blue. The ball is shown in white. The velocity vector of the players are also shown with arrows. As a result, we succeeded the learning tactics using this system. However, it turned out to be difficult to implement in a robot with velocity vector. So as a result, we have succeeded in mapping the relationship between the player positions and output the velocity vector. However, when implemented in a robot, it's hard to determine behavior from behavior vector alone. So also we do a second experiment. In this second experiment, we let the system learn the robot behavior. The purpose is to clarify whether the role of each player is shared throughout the team. By producing this next action as an output, it is compared with the results clustered by the robot, calculated by the robot. Specifically, it outputs the behavior categories. This action category is designed to be more aggressive as the behavior algorithm selection increases. This graph compares with the result with player numbers first and second. The result calculated by the system is shown in orange, and the result calculated by the robot is shown in blue. As a result, we have succeeded in mapping the relationship between the player positions and output the behavior algorithm selection. Using this behavior algorithm selection, it is easier to implement in the robot. Finally, until now, we have been made to appear to act in concert, but in order to play soccer with humans in the future. The gap between human and robots must be bridged. We will continue to work toward the realization of robots that can recognize human behavior and move flexibly. Thank you.
Okay, thank you, team Hikino and Musashi. Question time, please. Any questions?
No, Miko. I have a question. Yeah, have you considered the role of the robot? The role of the robot.
Yeah, sure. I also consider about a method like alpha, gamma, beta. So this player one is actually is alpha. So this one is a very active player. And player two is beta. So usually this robot try to position to the receive the pass. So,
okay. Yeah, thank you very much. It's very interesting. Yeah.
Really? Thank you very much.
I think that yeah, the robot should decide their roles by themselves. Yeah.
Thank you very much.
Thank you.
Any more questions? Any more questions? Any more questions? Okay, thank you, Team Hibikino Namasashi. Now we have finished our 4 teams presentation for scientific challenge, and according to the schedule table, next we will start our video challenge. The video challenge will start at 5 minutes later. 5 minutes later. So the first team will be Hibikino Musashi. So please get ready for the video challenge. Thank you. Okay, let me introduce the rules of video challenge of Middle-sized league this year. Video challenge is a special challenge in this RCAP 2021 Middle-sized league because we never have this challenge before. For video challenge, the video should more than 5 minutes, and we need to show something we want the team to show in this video. The video should have at least 3 parts of information. The first is the basic abilities of the robot and the video clips of participating in competition in recent years. The competition is not only the Robot Cup World Cup and not only in, for example, the RCAP or Robot Cup International competition. We want to see all the competitions, something like the national competition, the demonstrate, and the friendly match, and something like that. So we want to see more active RoboCup competitions all over the world. And the second part, we want to see other research results of the laboratory of our research team in the direction of robotics, which means this research result is not only with the RoboCup robots. We can the team can show something research on the other robotics platforms and other research, any research about the robotics they want to show in this video. And the third part is the content that needs to be displayed in the promotion of robotics and the scientific popularizations, which means the team maybe have done some work to science popularization and public for middle school or maybe young school student, various forms of robotics promotion activities, something like that. So for this video challenge, we have different items to evaluate the video. The team leaders has already get the score table. They can score the video according to the score table items. And we have 4 teams. We have different order to give the video challenge. The first is sorry, I will share my screen. The first is Hibikino Musashi. Team Hibikino Musashi, are you ready for the video challenge?
Yes.
Okay, during the video challenge, if you want to say something to explain the video, I think you can. This is also for all teams. If you want to say something to explain what happened in the video, you can. But pay attention that the sound, maybe you have a music or sound in your video, and you pay attention to the different sound to affect the video. So for the first team, Hibikino, you have 5 minutes for setup. You can test, or maybe you can share the screen and wait for the time for your challenge.
Thank you very much.
maybe so. Fei said,
Okay, Team Hibikino Musashi, if you are ready, you can play your video. Thank you.
Thank you very much. I will start.
Hi, how are you today? This is Hibikino Musashi World News. I'm Shuhei Nohara. How about today's content? Oh yes! So today I will show you Hibikino Musashi basic ability of the robot. Participation in competition in recent years. Research result and promotion of robotics. Scientific popularization. So Moiko is there to cover the news. Hey Moiko!
Hi, thank you Shuhei. Here is the latest report from Hibiki no Musashi. Musashi robot can do all basic abilities like getting the ball, dribbling, avoiding the obstacles, and also making a pass. In the game, we also can do all set play. Of course, goalkeeper robot is always defending our goalpost. Next, I will show you our participation in competition of robotics and scientific popularization. Every year, we tried to join several competitions, not only domestic, but also overseas. In 2019, we joined to the RoboFest. It is a big robot festival. And the next day, we won at Japan Open 2019. So, now Hibiki no Musashi is champion of Japan. Also, every year, we demonstrate to convey the interest of robots to children in children's hall, and a big shopping mall. Saka robots have been reported on several local TV shows. Musashi Soccer robot does more than just play soccer. We hold a marathon relay race every year. This is a very interesting event where people, animals, and robots run towards the same goal. We are also working to return the elemental RoboCup technologies to society. For example, we are working to utilize wheelchairs with an omnidirectional movement. Let's do our best anytime.
Thank you, Moiko. Did you get the interesting information of Hibiki no Musashi? Then that I would like introduce the other research result and promotion of robotics, also scientific popularization. Let's get started. Thank you. basic technology. Now, let's start with the educational programs for other technologies that are required before you can participate in RCAP. The first robotics education program we will introduce is the PicoEV Eco Challenge. This video was aired on a local TV program. Now, here it comes. This is PicoEV that runs on 7.2 watts. This robot is being developed to think about how we can save energy consumption. We are also using to run design methods and basic material mechanics in order to be able to carry a single person. This robot can be traveling about 2.5 kilometers in 30 minutes. Final goal. We try to develop the extreme low energy robots. Yeah!
The next robot education program, we will introduce a small robot. As we know, in a middle-sized rig, the robot must be equipped with all the sensor, microcontroller, kicking mechanism, and so on. Therefore, in a middle-sized rig, sensing technology, autonomous behavior algorithms, and embedded technology are important focus for winning. So, we are using RobotSumo to study these technologies. RobotSumo is one of the most famous battle-style competition in the world, with over 4,000 participating robots. Our team won the title of Yokozuna champion in 2017. The robot uses magnets to keep them from leaving the battlefield. Suction power is over 300 kilograms. We are using this technology for research in collaboration with a company to create robots that can climb walls and clean in slopes.
Field robot. Next, we will introduce the tomato harvesting robot. Our team is also running a competition to promote the development of robots that can act in natural environment, as well as robots that can act autonomously in dynamical environment, such as RoboCup. This table shows the specifications. The robot detects tomatoes in image processing, and this robot thinks about which tomato is the most easy to harvest. Next, we are promote competition for the junior division as an effort to train the next generation. We use Lego Mindstorm EV3 robots.
Lastly, I would like to introduce an underwater robot. This one is also active research in field robotics. Currently, we are working on a robot that can move to a waypoint and perform autonomous behaviors for oceanographic research. In fact, the robot has success to take photos and captured underwater creatures.
How was it? We introduced our team's soccer robot and related robot. We hope to share our various technologies with you. Okay, see you soon.
Thank you very much.
Okay, thank you, Team Himikino Musashi. It's time for questions. Thank you. We have 5 minutes for questions.
I have a question.
Yes, please.
Thank you for the very fun video. I was surprised by very high quality videos.
Really?
I have a simple question. How many challenge projects are there in your team? And how many people are working on each project?
About how many project is, yeah, I cannot count, but at the Takemura laboratory, maybe over 10 project.
10?
Yeah, and Ishii laboratory is more than Takemura laboratory, so too
Oh.
much, I think.
Yes, now I have the 10 over the 10, so very complicated. And now it's project. Maybe but almost 20 members in now it belong to this kind of project.
20.
Yeah, 20.
Very many people.
But mainly is maybe 3 competition we promote: the tomato harvesting robot, and also the ekiden. This is some marathon race, and also some drone competition, and underwater robot is mainly without in the RoboCup.
Unbelievable. Thank you.
Thank you very much.
Any more questions?
I have some questions about the tomato harvest robot.
Yes.
Yes, I'm curious about is it check the tomatoes, which is the ripped, or check the tomatoes are ripped and grab it out, or only the check?
No, we are we are check and how much this is how much good or not, and also we are harvesting and how much damage it or some how much this is good is also totally we are whole behavior to harvesting autonomously.
Okay, I know. Thank you.
Yep.
We still have time. More questions. Okay, thank you, Team Himikino Musashi. And next team should be the Dagozilla. And team member from Dagozilla, could you please enter the competition room for your video challenge? Thank you.
Yes, I'll be showing a few.
Okay.
We are Tim Dagozilla from Bandung Institute of Technology, Indonesia. We consist of undergraduate students as active members and some alumni as team advisors. We started our journey in 2016, where we participated in a national exhibition of mobile soccer robots. In 2017, we competed in our first national robotic contest. On a daily basis, we develop our robots for competition purposes. We also do some research to make fine improvements on our robots. We continuously strive to work on our robots because we want to improve our skills. That way, we will be able to fulfill our dream, that is to win competitions and take a step ahead toward the RoboCup 2050 roadmap. Here are our robots. We now have 2 fully functional robots, namely Jacobi and Kirchhoff. The other 3, Isaac, Laplace, and Maxwell, need to be repaired in order to play. Our robots, in general, can be divided into 3 subsystems: sensory system, moving parts, and controller. Sensory system is responsible for sensing the field and the robot's surroundings. It consists of a camera, proximity sensor, orientation sensor, and some motors encoders. While the moving parts consist of motors and a kicker, the controller consists of a microcontroller and a PC. These subsystems work together very well, creating more specific functionalities such as robot's perception and localization. Here are some of them. For the kicking mechanism, the robot can do 2 kicking modes, parabolic and straight, which is controlled by a servo connected to the lever. With these robots, we have competed in several national competitions and won some prizes. To advance in the development of the robots, research is a must. These recent years, we have done some research not only for the competition robot, but also for robotics in general. This is our telepresence robot. Telepresence robot is a robot which is developed to enable a person to virtually attend meetings, lectures, etc. The concept is just like a video call. The main difference between a telepresence robot from a normal video call is that the operator can control the robot to move through an Android application. Here, we show our competition-related research. Our research varies from mechanical, electrical, and programming things. In electrical, we did research on topics such as external encoder, locomotion system, as well as its control and kinematics. While mechanical crews explore the keeper expanding mechanism, ball dribbling mechanism, and robot vision. As for programming, we simulate the robot's vision and strategy. In these years, we also take part in ISRSC, Indonesia Symposium on Robotics System and Control. Here, we show the paper we submitted in 3 ISRSC events from 2017 to 2019. As a team, we understand that robotics has been doing great job to us. However, we are still far from the limit. Therefore, we want to share our knowledge about robotics to people around us, so that we can accelerate robotics development in Indonesia. Our short and informal survey shows that AI has been one of the most attractive topics from the perspective of commoners. Also, in this era, AI has been a really great success in lots of ways. Therefore, we can utilize this as the entrance to introduce science, engineering, and especially robotics. In our robot, AI has been playing a very significant role, especially in strategy development. This lets the robots have their own perception and decision. In just 2 years, AI has managed to bring us the Best Strategy Award in the 2019 Regional Robotic Contest, and even the Elite Four title of the National Robotics Contest in the same year. Not only in robotics, AI in general has brought humanity closer to ease and convenience. For example, in 2019, the business adopting artificial intelligence had grown by 270% in 4 years. The use of AI is enabling review and translation of mammograms 30 times faster with 99% accuracy, reducing the need for unnecessary biopsies. 46% of US adults use digital voice assistants to interact with smartphones and other devices. Artificial intelligence facts show that Netflix recommendation engine is worth $1 billion a year. Even in handling world-level threats, COVID-19, AI has helped us and is getting us to the end of this pandemonium. And we also hope that this advancement will carry on, creating a future for better. For that reason, learning AI is very important. We may start it with robotics.
Yeah, that is all for the first video. We're gonna show the second video app.
Okay, please.
This video about our basics, our robots' basic abilities. I guess that is all from us. Thank you.
Thank you, Team Takazera. It's time for questions, please. Any more questions? Any questions?
Okay, so I'm Yasunori Takemura. So in the Indonesia, how many team is participate in some domestic domestic competition?
There are a lot of teams. I guess it is about 50 teams.
15.
50. 50. 50.
50. Wow. And also, you have you get a champion or some good ranking?
I'm sorry, can you repeat your question?
So do you get some good result in the domestic participation competition?
Yeah, when it was an offline competition, it was just 2 years from our start of development, and we had deal for title at the National Robotics Contest.
Okay, thank you very much. And do you have some shared some children or something to some show that your robot or something?
Currently, we don't have any.
Okay. Okay, thank you very much.
I have one question.
Okay.
I'm not sure. For this year, 2021, do you have a national competition in your country?
Yeah, it was held online, so Yeah, it was not cup like at all.
I mean, you have a on-site competition now or not? Competition, on-site competition for this year or not?
For sure, we don't have any of them.
Okay, thank you. Okay, thank you team Dangazela, and for next team Iris. So team sorry, team Iris, you can play your video as you wish. Thank you.
Iris is ITS robot with an intelligent system. This team focuses on soccer robot development. Our robot has many abilities such as passing, kicking, obstacle avoidance, positioning and dribble, and also keeper defense. Iris has joined a lot of competitions such as Contest Robot Indonesia and RoboCup. On Contest Robot Indonesia 2021, Iris got second place and best design.
Juara kedua, Iris, Institut Teknologi 10 November. Desain terbaik, Iris, Institut Teknologi 10 November. Maka diputuskan juara umum Kontes Robot Indonesia tahun 2021 adalah Institut Teknologi 10 November. Terima kasih.
And then, on Contest Robot Indonesia 2020, Iris got first place and also best design. And then, ITS also got General Championship for 4 years in a row. For your information, Iris not only participate in competition but also contribute in the health sector to help nurses, especially during the pandemic, with Raisa, or robot medical assistant, and Violeta, robot ultraviolet. Raisa can help nurses on doing their tasks such as bringing many items, measuring the patient body temperature and oxygen levels. 22 units of Raisa has been used in 17 hospitals in Indonesia and still increasing its number until now. Besides Raisa, Iris also contribute at the development of Violeta, robot which has the ability to sterilize a room with UV light. In addition on conducting research and development on robots, we also have a program to introduce the world of robots to students with the aim of increasing their understanding of the world of robots. This year, it was held at MTS Nurul Islam. Okay, that's all from us. I think enough.
Okay, thank you very much. Any questions, please?
Hello, I have a question. Yeah, I'm very interested in your robot in COVID in COVID 19. So what it can do? What can it do? What can it do? What can the robot what can the robot do to defend the virus?
Okay, thank you for your question. I will answer it. Our robot Raisa have abilities to help nurse to bring in many items and then checking patient temperature and oxygen levels. So, and then Violeta has abilities to sterilize a room with UV light. Thank you.
Okay, thank you.
I have a questions. I see in your video you show a video in some competition which one person passed the ball to another robot and the robot passed to another robot and then shot to the goal. This is a challenge online challenge or a scientific or technical challenge.
It had a technical challenge, but offline.
Offline. You mean in
Site, yes.
So for all the teams, they will take the same challenge. It's a technical challenge, right?
I mean virtual live streaming on YouTube. and the another team get the same challenge as we get.
Oh, okay, thank you. Yes, this one. For every team, this challenge is in their own institution, or they come to a same place and take this challenge on site.
In our university, Institut Teknologi 10 November Surabaya, Indonesia.
Okay, thank you. Any more questions? If no more questions, thank you, Team Iris, and the next team will be the RV Infinity. Sorry, RV Infinity. So team member of US, you can go back to open room. Thank you. Team RV Infinity, could you please go into the competition room and get ready for the video challenge? Thank you. I think if you are ready, we can start the challenge right now. Are you ready?
We are ready.
Okay.
So I will start the video now.
Wait a minute. I will share this screen to the open room. Okay, you can start your video. Thank you.
Okay, thank you. Hi everyone, I'm Kevin Ricardo from RV Infinity, and today I will be presenting about improving distance estimation based on sensor fusion system. First of all, I will be introducing a little bit about our team. Our team was named RV Infinity and was founded in 2008. We are from Tokyo Polytechnic University Robot Vision Laboratory. Our laboratory is focusing on developing and doing research in vision system. Since then, we have participated in RoboCup competition, focusing in middle-sized league. Here is a picture of our team in RCAP 2019. This video shows the basic abilities of our latest version robot. To compete in RoboCup middle-sized league, a robot must have basic abilities playing a soccer game like a human, such as dribbling, kicking the ball towards the goal, and passing. The robot makes this decision autonomously by using computer vision. Here is how the self-localization of the robot works. How our robot recognizes obstacles, avoiding upcoming obstacles. This is an example of different gameplay action. Each robot has a specific role such as striker, forward, defender, and goalkeeper. Next, I will be presenting on the main topic of this video challenge about our latest research. In RoboCup, understanding the position of objects, such as robots, balls, play an important role in robots' movement and game strategy. In this case, an omnidirectional camera was widely used as the main system to recognize and estimate the distance of the object. However, by just using this single system, it lacks in distance accuracy that affects the gameplay. So the purpose of this study is to accurately estimate the distance of another robot by applying sensor fusion system. The conventional method is by using omnidirectional vision system. This vision system is located at the top of the robot that consists of hyperbolic mirror and a camera. This system is able to capture 360 degrees angle views by pointing camera upwards to the hyperbolic mirror. This figure shows images taken from omnidirectional camera. To recognize robot, we segmented black color and mask it with field area. Then each black feature, which is the robot, was searched radially from center of the image. The image pixel was counted and converted to actual distance. This table shows the distance estimation when target, or in this case another robot, is placed from 1 meter to 7 meters. From this result, significant amount of distance error was shown from this method. To solve the issue shown before, we propose a new method called sensor fusion. Sensor fusion is by combining two new sensors beside omnidirectional camera. The first sensor that we use is a depth camera. This depth camera is using IR stereo technology that can measure from 0.4 meter to 20 meters. Next, the second sensor is a LiDAR. This LiDAR is a 2D scanner that can measure from 0.06 meters to 10 meters. The field of view of depth camera is 86 degrees, where LiDAR is 270 degrees. In theory, by combining these two sensors, it can cover 360 degrees, just like an omnidirectional camera. This figure representing each sensor field of view. And next is the actual robot. That camera is placed to cover 36 degrees front view, and LiDAR is placed to cover 270 degrees rear view. Although this system has a dead zone of some degrees that can't be covered. Next, what is a depth camera? A normal camera can capture a color image that every pixel contains RGB value. Besides color image, depth image can be obtained with depth camera. Every pixel of this image contains distance value from the camera and represented by color. The red color represents the closest distance, where the blue color represents the farthest distance. From this color image, we do the traditional image processing to recognize robot. Then, the calculated robot coordinates were applied to depth image, then were converted to 3D point cloud, where actual XYZ coordinates can be obtained. Next is the second sensor LiDAR. Because LiDAR is 2D scanner, it needs to use an omnidirectional camera information for object recognition. In this figure, there are 3 robots to be recognized. Each recognized robot's angle then was mapped, and LiDAR was used to measure the distance of the object. To compare the accuracy of each sensor, we conducted a distance estimation verification. This experiment shows the distance error of each sensor when recognizing the distance of another robot. The table shows the result when the target was placed from 1 meter to 7 meters. From this result, the distance estimation of the new sensors was reduced significantly, or in this case, more than 10 times compared to a conventional vision system. After applying the sensor fusion to our current system, we conducted a verification on the actual soccer field environment. The result shows estimated robot position in a field with slam of the main robot. The robot is placed at the center of the field and a total of 3 targets around it. This figure shows omnidirectional camera result, where the red box represents target position and the blue box represents the estimated target position. In this result, we know that the estimated target position is off from the actual position. Next is the sensor fusion result. Comparing to the omnidirectional camera result, sensor fusion has lower distance error. This table shows the error of each target in details. In conclusion, sensor fusion result is more accurate compared to the conventional method. Next, this video shows how each sensor and sensor fusion performs in real time. This is when only a LiDAR sensor is used to map two robots around it. The mapping result is shown here. Next is when only a depth camera is used. We shot this video in a 6x8 meters field. This is final result of sensor fusion performed in real time. Note that the self-localization error of the main robot is included and affect the targets of mapping error. Lastly, to summarize this study, we applied depth camera and LiDAR as sensor fusion to 2D middle-sized leg robot. As the results, distance estimation was improved significantly compared to the omnidirectional camera. For our future works, we are planning to develop LiDAR's robot recognition without using omnidirectional camera information. I'm planning to develop object recognition using deep learning. That's all. Thank you for watching.
Okay, thank you, RV Infinity. Any questions? Any questions?
I have a question.
Yes, please.
Yeah. What do you want to add the LiDAR as your dual sensor? Yeah.
Can you repeat the question? What
Yeah,
we want to?
Why do you would like to add the LiDAR as your dual sensor?
We want to improve the distance estimation or improve basically the accuracy, the object recognition accuracy.
Yeah. Another question. Yeah, another question. In the video you mentioned that you apply slime to build up a map to location your robot.
Yes.
Yeah.
We
How about
applied. We applied the main robot SLAM to the self location of the main robot and then calculate the field coordinates of the detected object.
Oh, okay. How about the map from SLAM and how about the area? How about the accuracy of the map built by the SLAM and the real environment? How about the error?
So the error of the SLAM is included up to some degrees, maybe 20 centimeters or something like that. And then that also affect the robot's coordinate in the field.
Yeah. Okay. Thank you very much.
Thank you very much.
Can I ask?
Yes, please.
Thank you. Thank you for your presentation. It's very interesting.
Thank you.
Yeah. I want to know also the other project, or for example, the other festival or some participated competition. If you have some demonstration or something, I want to know.
We also have participated in Micromouse, which is a robot that searches for a maze and then line trace, and also sumo robot.
I see the line trace and the small robot. Then
Yes, and micro mouse.
micro mouse. Oh,
Yes.
thank you.
Thank you.
And do you have some teaching or children or some that shows some robot in outfield?
No, currently we don't have any projects around that area. I'm so sorry. We only have a demonstration for kids that we have.
So you are some demonstrating the kids?
Yeah, demonstrating to kids in RoboFest. RoboFest that we do in 2019.
So this, what is RoboFest? This is some big event of how many people coming in this kind of event?
Around 5,000 people have come in our event.
Okay, 5,000. Wow, very big.
Yes.
Okay, thank you very much.
Thank you.
Any more questions? Okay, thank you team RV Infinity.
Thank you for your time.
And now I will go back to the first page. Up to now, we have finished all the two challenges, scientific challenge and video challenge. So according to the schedule, we need to calculate the final score. So we will publish the final score by mail to send to all team leaders. And according to the information from the organizer, I will inform all teams about the award ceremony. The award ceremony will be held on Saturday, 28, tomorrow, from 14:40 to 16:30 Japan time. There will be a live streaming in the website, and I will publish the link of the live streaming in the mail of the final result. And the video of this challenge will be also published in the channel of RCAP 20 and 21. There will be a channel for all the leagues, and I will make some edit about this video, and I will upload to the YouTube channel and send the link or file to the organizer. They will publish in the channel of RCAP 20 and 21. And I will also publish the link and share all the point and the video we shared today to all the team leaders. So I think that's all for today. Thank you very much, and especially we need to thank the organizers of RoboCup and RCAP 2021, and thank you Moiko, thank you Takamura, and thank you all team leader and team members. Thank you for your work for this very difficult online challenge. Thank you.
Okay, thank you very much.
And Takamura and Moiko, I think we still live in the competition room, and we will discuss about the final result, because we need to calculate and double check. Thank you. All other team leaders, and we should also thank you Xinzhe Lü and Zhiqian Zhou. They are from Team Water and Team Newbert. They are the TC member and the EC member of Middle Size League. So thank you very much. I suggest if you are okay, we can open our video and we can take a picture.
Okay.
Our team leaders, we can share, we can open the video, we can take a picture. I mean, in the competition room, Moiko, competition room. Okay, thank you very much. First, I will take a picture by my mobile phone because I have lots of equipment here together. Okay. Now I will make a print screenshot. 1, 2, 3, cheer. Wait a minute, I need to double check whether we have the screenshot. Okay, thank you very much. And I wish to see you next year in Bangkok next year. See you. And Moiko and Takamura, we needed to discuss about the final score and other team leader or team members. See you next year. Thank you.
Okay, thank you very much.
See you, Liu, but I want to ask something.
Yes, please.
The final result will be shown today or tomorrow?
Pardon?
Hello?
You mean the award ceremony or the result?
Yes.
The result will be public at tonight. At tonight.
What time?
Give us more time to calculate. We need to double check. Thank you.
Okay, thank you. See you.
I think it's not too much time. Not too much time.
Yes.
Okay.
Okay. Thank you. See you, Liu.
Thank you. See you.
See you, Takamura.
See you.
See you.
Thank you very much.